Today I'd like to review with you some of the major ideas we covered in our unit on circuits. Tomorrow we'll do some practice problems together, and then the next day we'll go through our actual quiz on this unit. Okay, so we have two super important terms, voltage and current. Remember that voltage is a measure of energy per coulomb of charge. So in the battery, the chemical reactions produce a certain amount of potential energy for the charges. That's the voltage. The current measures how quickly the charges are flowing, how many coulombs are flowing past the spot per second. When you combine the two terms together, you get joules per second, or power. You multiply current times voltage, you get power. Remember, the fourth important term is resistance, the resistance of a wire or other object. The factors are the length, the area, and the type of material. When we combine them together, resistance of the wire, voltage of the light bulb, current flowing through would be I equals V over R, and the power is voltage times current. So the independent variables are your resistance and your voltage, and then the current and the power are a result of those. So more voltage gives you more current, and more resistance gives you less current. Then we learned this year how batteries age and become less useful. We talked about the internal resistance being the slope, the electrochemical potential being the y-intercept, and the maximum current being the x-intercept. We saw how wires did not quite behave the way we expected. That is, their resistance changed with temperature. So as the wire got hotter, the resistance got larger. We would get less current than we think we should because we got more resistance. We saw that this was a very complicated relationship and it was different for every single material. We saw that we could hook things up in series, that is one path. And we saw that you add up your resistors to get your total. The voltage you gain in the battery should be the voltage you lose as you go through all your different components. We saw that since there's only one path, the current is the same everywhere. And we saw that you would lose your most voltage in your toughest resistor. Okay, so these were all properties of series circuits. Parallel circuits were more than one path. The total resistance is less than your smallest resistor. So you don't add 8, 2, and 6. You would add 1/8, 1/2, and 1/6. You add the reciprocals. When you get your total, you flip it over, and that would be the resistance of all of them combined. We saw they all got the same voltage. We saw that the most current would go through the easiest path. We saw that you add up all your currents to find out how much came out of the battery. And again, we already talked about it. You add up all the inverses to get your total resistance. We saw that these ideas can be extended to any circuit using Kirchhoffs Rules, which said the current entering a junction is equal to the current leaving the junction. A loop around the circuit will give you a change in voltage of 0. Whatever voltage you gain, you're going to lose along the way. We saw that we can have compound circuits that have both series and parallel aspects. When you have a circuit like this, make sure 12 volts goes for the entire branch. 12 volts for the entire branch. Then you could find the currents in each branch by just doing the total for that branch divided by the total resistance. Once you have that current, you could then individually find voltages using Ohm's law, or powers using the VI equation. So don't make these hard. You only have two equations. The I equals V over R and the power equals VI. Just make sure you see that this series is connected to the battery, so it gets 12 volts. The bottom series also gets 12 volts. A little bit harder is when you have one like this. Now they have to share the 100 volts. So this plus this in terms of voltage has to give you 100. What you want to do is figure out an equivalent resistance for the parallel part. So you would do 1 over 80 plus 1 over 40. Get an answer, take the reciprocal of that, and that resistance would go right in here. You then find your total current. You then find your voltage here and voltage here. Whatever voltage is on this resistor is going to go for all parts of the parallel circuit. We then jump back into capacitors. We saw how they charged, how the negatives on the top plate push negatives off the bottom plate. We saw how the positives on this plate pulled more negatives onto the top plate. We saw that the current stopped flowing once we saturated our capacitor for that particular battery. A higher voltage battery could force more charges onto that plate. We saw that bigger area made a better capacitor, more room to store charges. We saw less separation made for a better capacitor. We saw adding an insulator made for a better capacitor because it was in essence bringing the positive charges closer to the negative plate without the risk of spark, without the risk of discharge. We then saw what happened when we hooked up multiple capacitors. We saw that in series, things got worse. It did have the advantage of allowing us to have a higher total voltage, so there's reasons to hook them in series. And then we saw that we could hook them in parallel, and things got better because in essence we were getting more plate area. We were able to get a larger capacitance and more total charge stored. We worked through the mathematics, and again, when you're talking about capacitors, it's the reverse of resistors. So even though these are in series, you get your total by adding the reciprocals and then taking the reciprocal of your answer. So you do it just like we do resistors in parallel, we do it for capacitors in series. Okay, capacitors in parallel, you just add the capacitances. So you just add those two. Remember, each capacitor gets the full volts because they're hooked up in parallel. When we were in series, these two voltages have to add to 6. They will not share it equally because they have different capacitances. The final thing is I want to make sure you understand short circuits. We saw this really briefly in this unit, but it's something they like to ask you about. So with that switch open, we would have a series circuit with these two light bulbs. And if they were identical light bulbs, that means each bulb would be getting 60 volts. They're designed for 120, so they'd be much dimmer than they're supposed to be. However, when we throw this switch, we short circuit this top bulb. Now the electricity is going to flow through this path. This is going to get the full 120, and that light bulb is going to be much brighter. We shorted out the light bulb in parallel. With capacitors, I want you to remember that capacitors start out empty and they act just like a wire with no resistance. But as they charge, they slow down the flow of electricity, and once they are fully charged, no more current's going to flow through that part of the circuit. So since we have a series circuit, when we first hook this up, the light is going to be really bright because this capacitor acts like a wire. But once that capacitor is charged, that light is going to be out. No more current is flowing through, so we would see that light dim over time and eventually go totally dark. However, if we have a capacitor down the bottom, when we throw the switch, it's going to start like a short circuit and this light will be off. But eventually this capacitor charges and no more current takes that path, and we're going to have that light get brighter and brighter and brighter until it reaches its full brightness. Finally, I wanted to give you the formula, so if you want to make a formula sheet to make it easier to find these things, we have the capacitor formulas, we have the resistor and circuit formulas. Current equals charge per second, voltage equals energy per charge. The formula for the resistance of a wire. Then we combine these terms together, we get Ohm's law, we get our power, and remember, power is energy over time. We have the formula for the internal resistance of a battery, and then our capacitor formulas, based on the physical properties, based on what it's hooked up to. Capacitors store charge, they store energy, and they create electric fields.